Imagine a computer program that can make decisions like a human expert. This is the idea behind rule-based systems, one of the earliest forms of artificial intelligence. These systems use a set of predefined rules to analyze information and draw conclusions. Like a detective solving a case, they follow logical steps to reach a solution. Rule-based systems were crucial in the development of AI. They showed that computers could mimic human reasoning, at least in limited ways. This opened up exciting possibilities for automating tasks that previously required human expertise. From medical diagnosis to financial analysis, rule-based systems demonstrated the potential of AI to transform various fields. At the heart of every rule-based system lies a set of if-then rules. These rules are simple statements that connect conditions with actions. For example, a rule might say, if the traffic light is red, then stop the car. These rules are based on human knowledge and experience in a specific domain. Rule-based systems are domain-specific, meaning they are designed to work within a particular area of knowledge. A system built to diagnose car problems wouldn't be useful for playing chess. The rules are tailored to the specific problem domain. This focus allows for greater accuracy and efficiency within that area. These systems are deterministic. This means that given the same input, they will always produce the same output. They follow the rules rigidly, leaving no room for ambiguity. This predictability makes them reliable for tasks where consistency is crucial. Additionally, their transparency allows humans to understand the reasoning behind their decisions. A rule-based system is like a well-organized toolbox where every tool has its place and purpose. It has three main parts: the knowledge base, the inference engine, and the user interface, each playing a crucial role in the system's functionality. The knowledge base is the storehouse of information, much like a vast library or a comprehensive digital database. It contains all the rules and facts that the system knows about the domain, meticulously documented and coded. This knowledge is carefully structured and organized, often in the form of if-then rules, ensuring clarity and precision. For example, in a medical diagnosis system, the knowledge base might include rules like, if the patient has a fever and a cough, then they might have the flu, providing a clear pathway for diagnosis. The inference engine is the brain of the system, processing and analyzing the information. It takes the information from the knowledge base and uses it to make decisions. Much like a human brain processes data to make informed choices. It matches the current situation against the rules and selects the most appropriate actions, ensuring the system responds accurately. It's like a detective piecing together clues to solve a mystery, methodically and logically. Finally, the user interface is how humans interact with the system, bridging the gap between human input and machine output. It allows users to input information and receive output, making the system accessible and user-friendly. This interface can be as simple as a text-based prompt or as complex as a graphical dashboard, catering to different user needs and preferences. Rule-based systems have found applications in diverse fields. One famous example is Mycin, a system developed in the 1970s to diagnose bacterial infections. Mycin used a vast knowledge base of medical rules to identify the likely cause of an infection and recommend appropriate antibiotics. Another example is Clips, a software tool for building expert systems. Clips provides a framework for defining rules, facts, and inference procedures. It has been used to create applications in areas like scheduling, planning, and monitoring. Troubleshooting systems are also common examples of rule-based systems. These systems guide users through a series of questions to identify the cause of a problem and suggest solutions. This approach is widely used in technical support and customer service to resolve issues efficiently. Section 5. The power of logic, advantages of rule-based systems. Rule-based systems offer several advantages that make them suitable for certain tasks. Firstly, their simplicity makes them easy to understand and implement. The if-then structure is intuitive, even for non-programmers. This transparency also makes it easier to debug and maintain these systems. Secondly, they can achieve high performance in narrow domains. When the rules are well defined and the problem space is limited, these systems can be highly accurate and efficient. They excel in tasks that require consistent application of predefined rules. Thirdly, the ease of maintenance is a significant advantage. As knowledge changes, updating the system is as simple as modifying or adding new rules. This makes them adaptable to evolving domains and ensures their continued relevance. Section 6. Facing the limits/disadvantages of rule-based systems. Despite their advantages, rule-based systems also have limitations that can hinder their effectiveness in certain scenarios. One major drawback is their lack of learning and adaptability, which can be a significant issue in rapidly changing environments. They can only operate within the boundaries of their pre-programmed rules and cannot learn from new data or experiences, making them rigid and unresponsive to new challenges. This makes them, inflexible in dynamic environments where the rules may change frequently, requiring constant updates and adjustments. Secondly, scalability can be a challenge, especially as the system grows in complexity. As the number of rules and the complexity of the knowledge base grow, the system's performance can deteriorate, leading to slower response times and increased errors. Managing and maintaining a large, intricate set of rules can become increasingly difficult, requiring significant resources and expertise. Thirdly, their domain dependency limits their applicability, making them less versatile. A rule-based system designed for one domain cannot be easily transferred to another, necessitating a complete overhaul for new applications. Building a new system for a different domain requires significant time and effort to define new rules and create a new knowledge base, which can be resource-intensive. Finally, performance bottlenecks can occur when the system encounters unfamiliar situations, leading to inefficiencies. If the current input doesn't match any of the existing rules, the system may not be able to provide a meaningful output, causing delays and frustration. This limitation highlights the need for robust exception handling mechanisms to ensure the system can manage unexpected inputs effectively. Section 7. Beyond simple rules, handling uncertainty and complexity. While traditional rule-based systems rely on strict if-then logic, researchers have developed advanced techniques to handle uncertainty and complexity in various scenarios. Fuzzy logic, for instance, allows for degrees of truth rather than absolute true or false values, providing a more nuanced approach to decision-making. This enables the system to deal with imprecise or incomplete information more effectively, enhancing its robustness in real-world applications. Another approach is to incorporate probabilistic reasoning, which adds a layer of statistical analysis to the decision-making process. By assigning probabilities to rules and facts, the system can make decisions based on the likelihood of different outcomes, rather than relying on binary logic. This is particularly useful in domains where uncertainty is inherent, such as medical diagnosis or financial forecasting, where precision is crucial. Furthermore, researchers are exploring ways to combine rule-based systems with other AI techniques such as machine learning to create more versatile solutions. This hybrid approach aims to leverage the strengths of both approaches, creating systems that are both flexible and powerful. For example, machine learning algorithms can be used to automatically generate or refine the rules in a knowledge base, making the system more adaptable and efficient in dynamic environments. Section 8. The legacy of logic, impact and future of rule-based systems. Rule-based systems have left a lasting impact on AI. They demonstrated the power of symbolic reasoning and paved the way for more sophisticated AI systems. Their influence can be seen in various fields, from expert systems and business process automation to natural language processing and robotics. While more advanced techniques like machine learning have gained prominence, rule-based systems remain relevant for tasks that require transparency, explainability, and the ability to handle complex logic. Their ability to provide clear justifications for their decisions makes them valuable in domains where accountability is crucial, such as healthcare and finance. The future of rule-based systems lies in their integration with other AI approaches and their application to new challenges. As AI continues to evolve, rule-based systems will likely play a complementary role, providing a framework for representing knowledge, reasoning logically, and ensuring transparency in decision-making. Section 9. Conclusion from rules to reasoning. Rule-based systems represent a fundamental stage in the development of AI. They demonstrated the possibility of automating human expertise by encoding knowledge in the form of rules. While they have limitations, their simplicity, transparency, and ability to handle complex logic make them valuable tools for specific tasks. Their legacy continues to shape the field of AI as researchers explore new ways to represent knowledge, reason effectively, and build intelligent systems that can solve real-world problems.